Hello everyone, I am Alessandro Ricciello and welcome to the Learning WebRTC Application Development video tutorial. Once completing this video, you will know the course contents and the various steps that will guide you to develop WebRTC applications. This video will clear any doubts about the course's argument and will show you what you learn and will be able to do at the end of it. To correctly understand all of the steps of this course, you should be a web developer with a working knowledge of HTML, the hypertext markup language, so the standard markup language used to create web pages, just a bit of CSS, cascading style sheet, the language used to describe the look and formatting of a web page. Then JavaScript, the computer programming language, which is part of web browsers, the implementations of which allows client-side scripts to interact with the user. Finally, you'll need a bit of knowledge about Java. It's an object-oriented programming language that will be used for backend development. And that's all. In this video course, you will learn the basic concepts of WebRTC technology and understand what its real features and purposes are. You will be introduced to the protocols involved in multimedia communication and to the appropriate use of the respective communication channels. You will learn the fundamental steps to build a real-time application, thanks to the Google App Engine and the WebRTC API. You will be introduced to WebRTC data channels and will be taught how to easily use them to create chat and file sharing functionalities. Finally, you'll discover just how simple it is to build a WebRTC application using the existing online wrappers. A wrapper is a third-party library that simplifies the work of the integration of complex API. So at the end of the course, you will be able to develop a fully working WebRTC application, publish your backend into the cloud thanks to the Google App Engine, and also increase your application's features by adding chat and file sharing functionalities. So what is WebRTC? Web real-time communication is a new technology that enables browsers-to-browsers application for audio-video calling, video chats, and peer-to-peer file sharing without any additional third-party software or plugins. Many times in this course, we'll refer to the term peer-to-peer. By the way, since we will always be dealing with browsers, the term should be browser-to-browser. In 2011, Google released it as open source, defining the fundamental architecture components. When implemented in a browser, these components can be accessed through a JavaScript API, enabling developers to build their own rich media applications. Multimedia communication over the Internet has always required well-defined installed software. Many proprietary communication solutions require software installation and configuration, so the user has to download additional software. That implies trusting the software producer, select only the needed components during the installation, and ensure that you have the right to install new software on the computer. All these steps only increase the time and complexity that the user has to go through before getting the communication started. WebRTC aims to be the standard solution without any additional software installation. The user will be prompted by a compatible web browser of media access, thanks to the HTML5 API. Then, the JavaScript app, written by the web developer, will interact with the browser through the WebRTC API. The user will not be prompted for any additional action or installation process. From the web developer's side, the browser will handle the most critical operation related to connection establishment and security mechanisms. Let's recap. WebRTC stands for Web Real-Time Communication, so it is a new technology for enabling browser-to-browser applications for audio-video calling, video chats, and peer-to-peer file sharing without any additional third-party software or plugins. It's made of a complete stack of audio-video communication with many additional improvements such as noise reduction, packet loss, and jitter handling. From early releases, it supports the latest VP8 video codec to better handle video compression. It also includes all the necessary techniques for connection establishment through NAT, which is Network Address Translation, and firewall systems. Even though WebRTC is a young technology, it has gained a lot of support from many developers and foundation. So, in a short span of time, the most widely used web browsers adopted it, increasing the number of supported features from time to time. At the time of making this video, only a few browsers didn't support WebRTC API functionalities yet. By the way, please note that you always have to check if your required functionalities are implemented in the various browsers. If a browser is declared as WebRTC capable, it could lack some new features because, as I told you, WebRTC is currently under development and something could change in the very near future. So why use WebRTC? Well, at the moment there are no complete solutions for multimedia communication using just a web browser. Plus, WebRTC is easy to use, high quality and cross-platform. To obtain something similar using the existing technologies, one would have to use Flash, Java applets, and a bunch of third-party plugins to make it work. Such solutions are usually heavyweight and difficult to implement and support. But WebRTC is free and open source. This means that you have immediate cost reduction and large community support for it. Finally, you can enlarge your ideas, imagine different applications, and implement them all thanks to this great technology. In the next video, we will see some example scenarios for WebRTC. Hello everyone, welcome to the second video of section 1 of the course. In this video, you will discover new projects that are currently using the WebRTC technology. Many new projects and technologies have to wait for many years to get loaded with features. This isn't true for WebRTC. It has in fact gained a lot of support from a very large number of developers, companies, and foundations. The key to success of WebRTC is based on various reasons. First of all, it's supported and sponsored by many companies around the world such as Google, Mozilla, and Opera. Then, it's one of the first working attempts to enter the unexplored world of browser-to-browser communication. WebRTC is also supported by a continuously growing open source community that keeps developing new features with respect to the IETF and W3C standard. WebRTC could be an opportunity to help small and medium-sized business activities, allowing customers to interact easily with our complex software installation. I will now show you some existing projects that you can take a look at to better explore the WebRTC world. Let's start with Zengaya. Zengaya enables voice calls through any computer, right from a web page. No download or phone is required. Zengaya's online call feature supports WebRTC, offering a new level of sound quality and user experience. Imagine allowing your customers to call you through your website. When shopping online, customers trust companies more when they can talk to a real person. Now OpenTalk. OpenTalk is a global service that enables you to add live face-to-face video experiences to any web or mobile property. OpenTalk is a flexible platform that exploits cutting-edge video, audio, and networking technologies such as WebRTC to bring the best experience possible to your browser or device through simple APIs. In 2012, the company that developed OpenTalk was acquired by Telefonica SA, which is a leading global integrated communications provider. Let's move to Asterisk. Asterisk is an open-source framework to build communication applications. It powers IP PBX systems, VoIP gateways, conference service, and other custom solutions. Asterisk is free, open source, and sponsored by Digium. It added support for WebRTC since version 11, although VP8 video codec pass-through support is only for versions above 12. As you can imagine, after showing the multimedia power of WebRTC, one of the main uses of this kind of technology is for multimedia communication. I will now show you some communication platforms that base their services on the WebRTC technology. Let's start with Emo. Emo is a free messaging, voice, and video call app that makes it easy for you to stay in touch with friends and family around the world. You can use Emo directly on the web or through a mobile device such as Android, iPhone, and iPad. Recently, Emo introduced WebRTC support that allows you to make seamless video calls without the need to download extra software or plugins to place a video call. Now, Meetico. Meetico is an innovative platform for internet-based collaboration. It provides high scalability and an enhanced quality of experience thanks to the seamless integration of heterogeneous media and collaboration tools using latest technologies such as WebRTC. A whole suite of tools, both from the server side and the client side, is available for seamless access to a fully fledged internet-based collaboration framework from heterogeneous devices, both desktop and mobile. Meetico is available both as a standalone in-house solution and as a service hosted on third-party facilities, that is, deployed on a cloud. Meetico is used on various online collaboration platforms. For example, it's adopted by IETF, the Internet Engineering Task Force, since IETF 80. Providing remote participation support at IDF meetings. A synchronized view of the official Jabber room, the current slides being presented, a shared note taking an editor and an audio-video stream from the room is made available in each Meetico room. The WebRTC web client wraps the Jabber room, lets you follow the slides being projected, and shows you an audio-video feed from the room. Audio and video are made available exclusively by means of WebRTC, and you can speak from the comfort of your couch if you want. Recently, Meetico was also adopted by a well-known innovative online e-learning platform called Docebo. Docebo is an SaaS cloud platform for e-learning, also known as a learning management system. Docebo is used for corporate learning and has interfaces with video conferencing and HR system. It has integration with CMSS's video conferencing software, Google Apps, WordPress, Big Blue Button, Vivoca, and recently integrated with Mythical to add WebRTC support. As you saw, the WebRTC world is continuously expanding, and we will learn how to easily manage this great technology. In the next video, we will see some of the network protocols involved in using the WebRTC technology. Hello everyone, welcome to the third video of section 1 of the course. In this video, you will discover the network protocols involved in a WebRTC connection and in the process of media exchange. To correctly establish a network connection through the IP protocol, it is mandatory that the initiator knows the remote IP address and that both parties reach each other through the internet. Every TCP/IP communication is defined by a couple of local IP addresses and ports and a couple of remote IP addresses and ports, so both the local and remote parts can identify themselves and exchange data packets. One of the most important parts of a multimedia communication is the connection establishment. WebRTC handles all the processes for you, finding the best method for avoiding NAT firewall limitations. As I said, one common problem of network connection establishment is NAT, which stands for Network Address Translation. NAT is often used to map one external IP to multiple devices in the same private network. This technique is mostly used in home or office networks, where we could have multiple devices but only one internet service provider network. NAT is based on a large table where the router makes a simple association between the external address and port and the local address and port. So virtually every client could, for example, use the same port, but mapped to different external ports. As you can see in the picture, while this technique could be useful in the client and server paradigm, when applied to peer-to-peer connection, it could cause many troubles and problems. So how can the two clients in the image reach each other if they don't know their real external address? They are both under NAT, so without using special techniques, they can't actually communicate. Another problem that might affect peer-to-peer connections is the firewall function of some router or work networks. As you can imagine, a firewall is a special element used to protect a private network from unauthorized access or to block the use of particular protocols. Imagine that some special rules configured on the firewall might block all the connections directed to non-standard ports, such as port 80 for the web and port 21 for the FTP. So the problem occurs again, as you can see in the picture. The two clients just can't reach each other. Fortunately, ICE techniques were created for this purpose, avoiding firewall and NAT limitations. ICE stands for Interactive Connectivity Establishment, and it's a technique for establishing peer-to-peer connections. As you can see from the picture, by applying this technique, the clients will collect all the available addresses, and it will exchange them with a remote part through a bridge server, using its favorite protocol. After this process, only the best candidate match will be chosen by each client for network communication. The ICE technique uses two different services for address discovery: STUN for avoiding NAT limitations and discovering external addresses, and TURN for tunneling all the network connections data by a relay system. Now let's analyze the STUN protocol. STUN stands for Session Traversal Utilities for NAT. It's a standardized set of methods that allow public IP address discovery. It permits NAT traversal for the application of real-time IP communications. STUN messages are usually sent in UDP, User Datagram Protocol packets. As you can see from the picture, you can imagine the STUN server as a reflector of the external address and port. So, before contacting the remote peer, the client will ask the STUN server which couple of external IP address and port it has. Then, the client will send a couple of IP address and port to the remote part. Basically, the client will use the same socket, so the same couple of IP address and port used for contacting the STUN server, also for peer-to-peer network communication with a remote peer. Finally, we can analyze the TURN protocol. TURN stands for Traversal Using Relays Around NAT. It allows clients behind the NAT or firewall to receive data over TCP or UDP. Useful in some NAT edge cases and to avoid blocking firewall rules, it supports a server-side authentication to avoid a service abuse. As you can see from the picture, you can imagine the TURN server as a tunnel between the two peers. The clients will contact the TURN server, authenticating itself and requesting for resource allocation, which in this case is a couple of external IP address and port. After this, the TURN server will keep forwarding the received packets until the session is alive. After invoking the service, the client will send the TURN server's external address to the remote peer. In this kind of scenario, the remote peer will send data to the turn server, which will forward it to the client, and vice versa. Pay attention, as already told in the previous slides, all these techniques solve only the NAT or firewall limitations. Most of the clients behind NAT or firewall networks will always need to exchange these just discovered external addresses and ports through some communication channels, for example, through an HTTP server. After correctly establishing a network connection, it's fundamental for both parts to handshake codecs that will be used for multimedia communication. WebRTC takes care of all this hard stuff for you. Both WebRTC peers should have access to a reliable communication channel. This kind of communication is mandatory for media handshaking. As you can see from the picture, to establish a connection, the two peers have to connect through a server that will act as a man in the middle. The server, in fact, will forward every message from user A to user B, and vice versa. This kind of message exchange is necessary for letting the peers negotiate the media codecs that they will use during the multimedia communication. As you can imagine, the method or protocol used to exchange messages is totally a choice of the developer. The media information needs only an envelope that can be sent from one peer to another. One of the most often used protocols is WebSocket. The WebSocket protocol provides bidirectional communication channels over TCP. It was standardized in 2011 by the IETF, the Internet Task Force Engineering Group. The API used in the browser was standardized by the W3C, World Wide Web Council. The WebSocket protocol was designed to be implemented in web browsers and web servers. As you can see from the picture, it uses HTTP only for first requests, where it uses the header field called upgrade to request a protocol upgrade to the server. The server will reply confirming the request by adding the same header field to the answer. With this kind of protocol, the server can send content to the browser without being solicited by the client. Plus, communications are done over TCP port 80, avoiding NAT firewall issues. Please note that using this protocol requires that web applications on the server support it. But actually, many browsers support it natively, for example Chrome, Internet Explorer, Firefox, Safari, and Opera. Another way to exchange data between browser peers could be AJAX. AJAX is not actually a real protocol, but it could be defined instead as a set of techniques used to send an asynchronous JavaScript request to a server. AJAX, as anticipated, stands for Asynchronous JavaScript and XML. While the XML word is quoted in the technology title and acronym, the usage of XML is not mandatory. In fact, JSON is often used instead. JSON stands for JavaScript Object Notation, used especially as a format for data exchange on the web. As you can see from the JavaScript snippet at the end of this slide, data can be retrieved using the XML HTTP request object built in natively in all the supported browsers. By the way, please note that sometimes the name of this object will change, so refer to the respective browser's documentation to double-check this. On analyzing the JavaScript snippet, we can see that first of all, a new XML HTTP request object was created, and then we define the URL to be called for the request and method to be used, for example, get or post. After this, we add an event listener function to this object, which will be invoked only when a response is ready to be read. We'll display an alert with a return text or an error checking the status of a request. In the HTTP protocol, the 200 response code means that all went well and the resource has been retrieved. Finally, we will call the send method on the XML HTTP request object to let the request begin. After learning some protocols that can be used to create a signaling channel, we can now define the protocols used by WebRTC to describe the media in the handshaking process. SDP stands for Session Description Protocol. It was proposed as a standard by IETF in 2006. This kind of protocol is intended for describing multimedia communication sessions, and it's often used for negotiation between the endpoints of media type, format, and properties. The group of media type, format, and properties is usually called a session profile. This protocol is often used in conjunction with RTP, RTSP, and SIP protocols. RTP stands for Real-Time Transport Protocol, and it's the same protocol that WebRTC uses for real media exchange. Pay attention now, we're talking about the real packet of media data, not the media description. RTSP stands for Real-Time Streaming Protocol, a protocol often used for media content delivery to mobile devices. SIP stands for Session Initiation Protocol. It's the main protocol used for VoIP session signaling, and it handles all the side information related to the VoIP word. Returning to SDP, as you can see from the snippet on the right side of the slide, every message is made of three main sections. Session, where we can find the protocol version, in this case 0, the origin ID, username, session name, and other description. Timing, which is the time relative to the current session, and media description such as media name, transport, type, and so on. We have now completed this section. You should be able now to know and identify the various protocols involved in one WebRTC communication. Even if you will not have to deal with all of them during the setup of a WebRTC session, you can now have a more clear idea of the WebRTC communication stack. In the next section, we will talk about backend configuration through the Google App Engine framework. Hello and welcome back. So far, we've got some basic understanding of the WebRTC standard and the network protocols. It's now time to learn the main features and most common uses of the Google Platform as a Service, Google App Engine. Even though WebRTC is a well-known standard, finding a way to build a backend could be really difficult. You will learn how simple it is to use Google App Engine to create a backend that will handle communication between two clients. Let's start exploring the main features of Google App Engine. Google App Engine is a platform as a service offering. It lets you build and run applications on Google's infrastructure. Platform as a Service is a cloud computing utility that provides a computing platform and a solution stack. It's a model of cloud computing where the end user creates an application or service using the tools and libraries from the provider. The end user also gets to control software deployment and configuration settings, while the provider provides the networks, servers, storage, and other solutions that are required to host the end user's application. Google App Engine supports apps written in a variety of programming languages, such as Python, Java, and recently the PHP and Go languages as well. An SDK with local test environment and deployment tools is available for App Engine supported languages. You can find out more about this SDK if you want at developers.google.com/appengine/docs/what-is-Google App Engine. Please note that App Engine's data storage and traffic is free up to 1 GB, but you can increase it by paying if you want. We will only be using a very small subset of the App Engine's features. Remember that a feature may be available in every runtime language or only in a subset of languages. So, before planning to use a feature, check if it's available in your preferred programming language. Every App Engine feature is classified according to its status and availability, as general availability, beta, and alpha. Let's check out App Engine Data Store. App Engine Data Store is a schemaless NoSQL data store for your web application. NoSQL databases provide different storage and retrieval methods for data handling. These kinds of mechanisms are totally different from the ones used by relational databases and could be really useful to improve performance on schemaless data. The App Engine NoSQL database uses atomic transactions, high availability, and a strong consistency. As anticipated in the course description, we will use Java as a programming language for developing the backend. We'll use the Java SDK shipped with Google App Engine, which uses a full Java runtime environment. App Engine runs Java 7 JVM in a safe sandbox environment, so please remember the following points. First, the App Engine application cannot write to disk, but it can only read its files. It has limited time of response, and it cannot use any other system calls. Second, an App Engine Java application can use threads paying attention to some restrictions. Google also developed a plugin for Eclipse that adds debug configuration and a testing environment. So, as you can see in this introduction, Google App Engine is a platform full of features that are ready to be explored. After this section, you will be able to set up a complete Google App Engine environment that will be ready to develop web applications. Keep in mind that App Engine is a Google's product, so it's well documented and tested. So in case of any doubts, please refer to the online documentation or to the available Google groups. As you saw, Google App Engine is an easy-to-use framework that brings all the needed stuff to make an advanced web service. In the next video, we'll introduce the Eclipse Java IDE tool configuration. Now, let's move on to configuring the Eclipse IDE to develop our App Engine-based backend. After choosing a reliable platform, the next difficult step is to figure out what kind of environment should be used for development. Let's talk about some common questions that come up while starting a brand new project with a new technology. First of all, we will be using the Windows operating system for our development. Don't blame me for using Windows instead of Linux or Apple OS X, because for this kind of development, the choice of operating system is all up to you, so you're free to use Linux or OS X if you want. Then choose your favorite IDE too. My choice is the Eclipse IDE from the Eclipse Foundation because it's a free Java-based software. Now I've created a dedicated Eclipse workspace to use throughout the course. The workspace is the main working folder for Eclipse, and this is where it stores project information to manage all the projects that you define in it. So create a new empty folder and select it from the next window. As told before, the main feature of Eclipse is its modularity. So let's install the Google App Engine Eclipse plugin to easily develop and test App Engine applications. First of all, we have to select the right plugin for our Eclipse version. Just point your browser to this URL and then choose the correct link. We'll choose the Luna version, Eclipse 4.4. Then copy the URL. After that, from the Help menu at the top, select Install New Software. Then paste the copied link into the first text box of the window and press Enter on your keyboard. Eclipse will now start querying the web page, retrieving all the available and installable plugins. After the web page parsing, Eclipse will show you the list of available plugins you can install. Now we need to select only the two main components, the Google plugin for Eclipse, which is, as you can see, is also marked as required, and the Google App Engine Java SDK. However, feel free to search the web for the main uses of other modules to explore the world of Google. After checking the previous two components, just click on the Next button as I did, and Eclipse will now calculate the required dependencies and it will show the result. In our case, the selected components don't have any dependencies, so Eclipse will install only the two modules. Just click on Next again. Then accept the license agreement and click on the Finish button. That's all. Eclipse will now handle all the complex processes for us. Eclipse is now downloading the required packages and it will extract them in your installation directory, allowing you to use them. Please note that if Eclipse will report an error on validating the package signature, click on OK and proceed with the installation. Upon completing the installation process, Eclipse will ask you to restart itself to let the modules be activated. Just click on the OK button and proceed. After Eclipse restarts, we have to check if everything went well. So click on the Help menu and click on Install New Software. After that, click on the link at the end of the window, which is named What is already installed. Then try to locate the two installed modules shipped to you by Google. Finally, let's check if the plugin installation also added the new project Eclipse template. So click on File, then click on New, and scroll down to click on Other. From the foreground window, search for a Google folder. Once you find it, just expand it and look for Web Application Project. And that's all. We discovered how to easily configure our Eclipse IDE for supporting Google App Engine platform. In the next video, we'll see how to obtain a Google App Engine App ID. Now that we have completed the Eclipse configuration, we will discover how simple it is to create a new Google App Engine web app thanks to the Google Online Eclipse utility. There is no special API or configuration to learn. You have to just follow a simple web procedure, take the just generated ID and place it on your Eclipse configuration. The App Engine admin console gives you complete access to the public version of your application. You can access it by visiting the following link in your web browser, appengine.google.com. Then, sign in with your Google account or create one with an email address and password. You can use the administration console for the following purposes: to perform basic configuration, such as change the application title, cookie expiration, authentication options, and so on; to set the application performance options in order to manage cost and performance; to view configured services; to set a new host domain; to disable data store rights; and to disable or delete your application. Now, we'll see how to create a new application with a free appspot.com subdomain or a top-level domain name of your choice. Start by clicking on the Create Application button at the bottom. You have to choose an application identifier that will be your subdomain name. The main domain will be appspot.com. I suggest you to check the availability of the name before proceeding. which you can do by clicking on the button just on the right of the box. Note that this identifier cannot be changed. Then you have to set an application title, which will be displayed when users access your application. After that, you can choose which kind of authentication to use for your application. Google offers 3 different systems to authenticate your application's users. Only one form of authentication can be used for a given application, so we can choose from Google Accounts, Google Apps Accounts, or OpenID provider. Or we can leave the default choice, which is Google Accounts. But please note that currently you cannot switch authentication options for existing App Engine apps to or from Google Apps accounts. Application authentication restriction can only be set at or shortly after app creation. Finally, we have to configure storage options. We can choose between high replication and master slave. High replication uses a more highly replicated data store that makes use of a system based on an algorithm to synchronously replicate data across multiple locations simultaneously. This offers the highest level of availability for reads and writes at the cost of eventual consistency for some queries. Master slave uses a master slave replication system, which asynchronously replicates data as you write it to another physical data center. So we'll leave the default option high replication, since master slave is deprecated and not recommended. After that, we're done. Just click on the Create Application button and wait for the result web page. The result page will show you the confirmation for the chosen ID and some recap of the chosen option. We can click on Dashboard link to go to the dashboard panel of the newly created application. The admin console dashboard has charts that give you a quick visual reference of your system usage. The information shows various snapshots of resource utilization and performance statistics over different time periods, depending on the particular chart. 2 pull-down menus above the charts let you filter the information by application module and version names. Instances are the computing units that App Engine uses to automatically scale your application. You can use the Instances dashboard to understand and control your application. Please note that App Engine applications are powered by any number of dynamic instances at any given time, depending on the volume of requests received by your application. As requests for your application increase, so do the number of dynamic instances powering it. Then, we can find on the same left menus some dedicated views for logs, uploaded versions, cron jobs, task queues, and quota details. Google Web Console also gives us the opportunity to control and view details on data stored by our application, thanks to all the views and dashboards under the data category. We can also manage advanced settings and billing options in case we choose some paid service. Now we're ready to take the generated ID and place it on our Eclipse project. We will now be able to deploy our first Hello World app. In the next video, we'll explore together the GAE Channel API to better understand its features and purposes and how it will be used in our project. In the previous sections, we introduced the Google App Engine platform and its main features. For our goals, we'll only use a few App Engine features, such as the Channel Data Store API. Together, we will explore the GAE Channel API in order to better understand its features and purposes, and to see how it will be used in our project. As we saw in the previous sections, we need a channel for media handshaking and some other data exchange. Forget about defining all the complex use cases to handle a data channel. Google App Engine, in fact, takes charge of all the complex things and lets you care only about the things you need. As you can read in the description, the Channel API creates a persistent connection between your application and Google servers, allowing your application to send messages to JavaScript clients in real time, without the use of pooling. This can be very useful for an application that uses real-time communications. Using Channel API, you can easily avoid losing time polling for events. You can define some callback that will alert you in case of changes. As already anticipated in the previous sections, the Channel API is used by 2 main components, one in the server side and one in the client side. We have already explained why we chose the Java programming language for the server side and JavaScript for the client side. Let's start with some examples. Look at the first. We can see how a client requests its token, giving its client ID to the server. Our App Engine server will generate a token thanks to the client ID and will forward it directly to the client. Only after that, the client will open a socket and start listening for incoming messages through the Google App Engine channel. Now we can move on to the second example. In this case, user A and user B have already defined and established their respective connection to our App Engine server. So, when client B sends a message to App Engine server, it will be forwarded to user A using the previously created channel. User A will be notified, thanks to the callback listening for incoming events on the socket previously opened. As you can imagine, this is the same scenario we could reproduce for our WebRTC application. In fact, user B could be the initiator of the multimedia communication, and its messages could contain information about the media codec to be used during the communication. Looking at the example on the Google App Engine documentation, we can see that the servlet requests the channel service, generates the token starting from the client ID, and then places it in the web page. Finally, the servlet will serve the web page just customized with the generated token. On the client side, thanks to the JavaScript code, the client will open the socket and then define the callbacks for handling events and the function for sending messages through HTTP POST requests. Applications may register for notifications when a client connects to or disconnects from a channel. This is the feature brought to us by Channel Presence option. Channel Presence is an additional feature that is disabled by default. In order to enable it, you should directly define it in the appengine_web.xml file, as already shown in the previous video. Keep such types of features in mind, because we'll need it to track users who will leave a communication prematurely. In that case, the server will inform the other party that the current user is disconnected. In the next video, we'll see how to create the first example app, using the powerful and easy to use environment that we have previously configured. In this video, we'll see how to create the first example app, using the powerful and easy to use environment that we have previously configured. You don't need to remember all the complex directory tree and config files to create a brand new project. Thanks to the Eclipse New Project Wizard, you'll be guided through the entire process. So, open up Eclipse by double-clicking on its icon. Remember, you'll find it in the directory where you extracted it. On the bottom right corner of the Eclipse window, click on the Sign in to Google button. Follow the process to log in your Google account and click on the Accept button. Then start creating a new project. Go to File, select New, click on Other, and then search for the Google folder. In this folder, select the project type Web Application Project and click on the Next button. Now start filling in the details in the next window by choosing the project name and the package name for our Java project. Choose the names you prefer. We don't need the Google Web Toolkit, so deselect it. Then we have to select the app ID we've just generated in the previous section. We can write it directly or select it using the Browse button. Don't forget to leave the sample code option checked. Click on Finish to complete the process. As anticipated in the previous sections, looking at the project structure, we can find similarities with a standard web project. As you can see, the folder looks like a servlet container project. We have a war directory, webinf directory, and so on. The just created main class extends HTTP servlet Java class. Just to customize the template class, we can edit the message returned by the servlet or try to change it into something fun and dynamic. So we can see that there's an engine in the backend and not just static content. I've prepared some text with a date to help you understand how useful it can be to have dynamic content. Now, just to better understand the global working mechanism, open the file named appengineweb.xml. You will find it under the war webinf directory. As you can see, the file is almost empty. It only contains some options to inform Google App Engine Framework to consider the app completely thread-safe, so it can be used simultaneously by many threads. This file also defines the position of the login properties. Now let's analyze the file named web.xml, which is located under the same path as the previous one. We can see, if you're familiar with web services development, that it defines the servlet URL mapping with the Java classes. In our case, we can see that our main class, named hello_world servlet, is mapped to URL/hello_world. In this case, no path is specified after the / symbol. The index.html file will be served and displayed. Also, open the index.html file to take a look inside. It only shows some welcome text and displays an URL moving the user to Hello World servlet. So we are ready to run the just created sample code. To do this, just click on the green play button, which we can find on the toolbar at the top. The console view at the bottom of the window will be filled with log messages reporting that the local server is being initialized and started. Just wait until you see the message info DevOps server is now running. Just some lines before the last message, we can see that the server address is printed on the logs. It should be something like http://localhost:8888. Just follow the link to see our dynamic content displayed by the servlet. Now that we completed testing the app, we are ready to deploy our sample project into the cloud. From the Project Explorer panel on the left side of the window, right-click on the project. Then click on the Google menu item and click on Deploy to App Engine. Finally, just click on the Deploy button. The tool will open up the App Start page automatically, so you only have to wait. Follow the link as you did before and check your app working into the cloud. We've just learned all the necessary stuff to configure Eclipse and to use the Google App Engine platform. In the next section, we'll explore the basic WebRTC API usage. We have just learned how to establish a signaling connection channel using the Google App Engine Channel API. Let's move on to understanding the basic WebRTC API and its main uses. Upon completing this video, you will discover how to easily access the MediaStream API's common functions, which are mostly used for user multimedia devices access. In the previous section, we inspected how to properly configure and manage our backend development environment. Now, we'll start seeing the first step needed to properly build a WebRTC-ready peer-to-peer client. As you can imagine, one of the most important steps before correctly establishing a full multimedia communication is to properly acquire access to multimedia devices, such as webcam and microphone. MediaStream API is a part of a WebRTC specification. It's mainly used to describe stream of audio or video data, and it defines the methods to interoperate with them. It allows to set the necessary callback to handle instances of success or error while using asynchronous methods and events. The web page you see is the current working draft of MediaStream API that is being edited and developed by W3C, the World Wide Web Consortium. The API helps you create a MediaStream object that represents a stream of audio or video data. A MediaStream object could typically be represented by a simple URL string, used as a reference for the real data, that could be stored in a DOM file or blob object. MediaStream objects could be divided into two categories, local or remote. Local object of MediaStream type is called local if it was generated through getUserMedia method. In this case, its source input is taken by a local microphone or camera. A MediaStream object could also represent a remote media element, originated through the network and obtained via the WebRTC Peer Connection API. Now, let's see a practical example of media resources request through a web browser. We'll develop a simple app that requests user media and will be displayed inside a video element in a static web page. Open the Eclipse IDE. Create a new HTML file, for example test.html, then start writing a typical structure of an HTML page. Please note that Chrome blocks a lot of stuff on the file URIs without reporting a security error. So our best option will be to serve the web page from a local web server. We can use the embedded Jetty server on the App Engine framework. To allow the web server to properly distribute our web page, we have to create the test.html file under the work folder of our project. For this kind of example, we can use the same project we created in the previous section. So right-click on the Word directory, then select New File, and write down the name chosen for that file, test.html. Then click on Finish. The Eclipse editor should open it up automatically. At this point, start writing a standard structure for a simple web page. We can use a very simple structure, composed of the head and body elements. We can now define the video object that is required to display images from the user's webcam, and the JavaScript container to access media devices through MediaStream API. We also need to set the autoplay tag to enable automatic playback when the SRC property will be set. Now we have to define the JavaScript code to request user media. We need to use the navigator object. Please note that the navigator interface represents the state and the identity of the user agent. It allows scripts to query the browser and to register themselves to carry on some activities. Since we want to use the Chrome web browser, we have to use the WebKit getUserMedia method to request all the required media. The first function's argument is the constraint on the media that has to be requested to the user. In our case, we only declare the video access as mandatory, because we want to display it into the HTML video element. The second and third arguments are callback functions, used in case of success or error taking media access through the web browser. As you can see, in case of success, we set the SRC property of video elements with URI of webcam video stream. The URL.createObjectURL static method creates a DOM string containing a URL representing the object given in the parameter. The URL lifetime is tied to the document in the window on which it was created. The new object URL represents the specified file object or blob object. In case of failure, we present a pop-up reporting the problem to the user. We grouped all these instructions inside a try-catch to eventually show an alert if the user will use a non-Chrome browser. So let's test it. Start the project, as we did before, by clicking on the green play button on top of the Eclipse toolbar. This will start the embedded Jerry servlet container that we will use for serving static HTML files as well. Now, we are ready to watch the result directly at localhost:8888/test.html. Then, you should see a pop-up just under the Chrome address bar that will request for media access. Once you accept to access your media resources, you'll see the webcam output directly in the window of your web browser. That's all. You learned how to use the MediaStream API to easily access media devices. In the next video, we'll talk about peer-to-peer connection establishment through the Peer Connection API. Let's move on to understand how to declare and initialize a peer connection object to start media handshaking and communication. After acquiring media access from the web browser, it is necessary to initialize the peer connection object through the WebRTC JavaScript API in order to start the communication process. The web page you see is the current working draft of the Peer Connection API. The version explained in the page is obsolete, but the diagrams are almost correct. The RTC Peer Connection object handles a WebRTC connection through efficient streaming of data between two peers. Please note that RTC Peer Connection and RTC Session Description are renamed in most browsers. So, to use them, you should use the correct class's name. For example, in Google Chrome, you have to use WebKit RTC Peer Connection. Looking at the first diagram in the web page, we can see that basic RTC peer connection usage involves, for example, negotiating a connection between your local machine and a remote one. The peers will communicate by session description protocol messages. For example, the caller sends an offer just after adding the local stream media, audio and/or video. The called party answers with its SDP to correctly start the handshaking procedure. Both parties, the caller and the called party, need to set up their own RTC peer connection objects initially. So, open Eclipse IDE and let's create a new HTML file to test RTC peer connection object. Please note that, in this example, we will develop both parties, remote and local, and they will be defined in the same part of a static HTML page. I know this could be a little confusing, but we need to understand that the browser really doesn't differentiate between local or remote parties. The whole process is handled by the WebRTC engine, and the only thing we should care about is to transfer SDP, session description messages, between the two parties. Create a new HTML file by right-clicking on the Word directory and selecting New and finally File. We can call the new file peertest.html. Eclipse should open it up automatically. So, as we've done before, define a basic HTML web page structure made by head and body tags. We also need two video tags because we want to simulate the media handshaking process and establish a full connection. We will use a div tag with a custom ID to log some output from the whole process. We are now ready to define the JavaScript code container. So, first of all, we have to define custom functions for handling log and errors printing. After that, we have to initialize the RTC peer connection object to start the media handshaking. So, first, we have to define the RTC peer connection object for Google Chrome. It is named WebKit RTC peer connection. Please note that if we don't want to really send the message to a remote party over the internet, we are not forced to define some ICE servers while we create the RTC peer connection object. So, we give the null argument during the creation. After that, we also need to define the callback for the ICE candidate. Even if we don't use any external stun or turn servers, we still need to define callbacks to allow peer connection objects to intercommunicate with each other. After that, we're ready to assign the newly created callbacks and to define the onAddStream callback in order to set up the remote stream when it will be available. Then, we have to request media access through the MediaStream API we have already used in the previous video. In the callback function, when the user's resources are just acquired, first we call the addStream method to add the media we just obtained from the browser to the peer connection object. It's because of this method the peer connection object will know which kind of media it will serve during the multimedia communication. After that, we have to invoke the standard method called createOffer that will inspect the resources added to the peer connection object through the addStream function. So, it will generate a SDP message describing those resources. In the body of that function, we set the local description for the peer connection object, creating a new RTC session description object. The RTC session description interface represents the parameters of a session. It consists of the kind of description, which is part of an offer-answer negotiation it describes, and of the SDP descriptor of the session. After that, in case of correct creation, we are ready to send a message to the remote party. In our case, we print a message in the previously defined log_div tag and save the result in a local variable. In this case, the peer connection object has to reply to the offer previously created. So, after adding the local stream, we have to call the setRemoteDescription method using the previously created offer request as argument. Then, in case of success, the peer connection object will create the answer. As you can see in the code, the newly created answer will not be forwarded to the local peer connection object through the network. Instead, the setRemoteDescription method will be invoked directly through the local PC object. As you can see, after correctly acquiring access to the media device, we can use the related stream for both parties. If you're asking why we inserted all the functions in each other, the answer is very simple. Since we're playing with asynchronous functions, by inserting one in each other, we are ensuring the right order of execution that we need. That's all. The communication should be available in seconds. So, we are now ready to test the newly created test page. Press the green play button you can find on the top toolbar and wait for the Jerry local servlet container to start. Now, using your Chrome web browser, go to localhost:8888/peertest.html and watch the result on the browser's window. Don't forget to accept the media access request that you'll receive through the browser. As you can see from the JavaScript output, you will find many lines full of data. However, if you look at the lines, you can identify media definitions for audio and video. For example, for audio, you will find the line RTP map PCMU/8000. This represents a type of audio codec. Also, the lines above and below will show information about the audio codec supported by your browser. For video, you have to scroll down a bit, and you will find some lines like RTP map VP8/90000. VP8 is the default video codec used by Google Chrome browser. The codec is a property of Google, but it was released as open source recently. Looking at the example layout, it seems that you have the same video on the local and remote side. By the way, there is a real communication in act. You can exercise placing some CSS property on the remote video element to flip the video container, or set a JavaScript timer to delay the video's autoplay and simulate a network transmission. But don't worry, in the next video I'll show you some useful tools that will help you check whether the WebRTC technology is actually running. So we're done. In this video, we learned the basic uses of the Peer Connection API through a very simple example. In the next video, we will talk about how to correctly handle errors in the WebRTC applications. So far, you've learned how to use the Peer Connection API. You will now learn how to debug your app, find errors, and handle properly any connections closing. While learning to use a new technology, one of the most important things is to properly use all the tools that it can give us. Moving back to the example shown in the previous video, what happens if we try to test it and it simply doesn't run? What can we do in case of a problem? Or when we want to inspect WebRTC components placed inside the browser and thus not directly accessible? Now we try to simulate a common problem, that is, the name mismatching. Open up Eclipse and locate the ICE local callback function. Then try adding some character before its name, for example an underscore. Now start the Jerry Servlet container if you haven't yet. Open the web page peertest.html and see what happens. Nothing, we have a blank page and we don't know how to debug or find the error. Please note, in case you don't see the change, you should try to reload the web page several times. You can do it by pressing the F5 key on your keyboard multiple times. Chrome in fact could cache the previous version of the web page. Now we'll see how simple it is to find bugs in the JavaScript code. For this purpose, we could use the Chrome integrated console to check whether any errors occurred. To show this console, you can right-click on the page and click on Inspect Element. As you can see from the HTML code displayed at the bottom of the window, the page is not actually blank. It could be a problem in the JavaScript code, since neither the video tag nor the div tag were populated at all. So move on the Console tab, the last part of the window. We have found the error. As reported by the JavaScript console, the JavaScript interpreter can't find the function named ICE local callback. This error occurred because we renamed our function. The JavaScript console is often used by web developers, but what happens if the problem is not caused by malformed code? Will we see any error on JavaScript console? Luckily, Chrome offers a nice panel to monitor our active WebRTC sessions. First of all, we can put a bug inside the code to allow the failure of the initial communication process. Open Eclipse, correct the previously introduced bug, search the line where we assign on ICE local callback to the local peer connection object, and then comment it. After that, go to the browser and reload the web page. As you can see, the result is different from the previous one. Now we have two black video screens, some output in the log div tag, and so on. So what went wrong now, and how can we verify it? Open a new Chrome tab and go to this address, chrome:/WebRTC-internals. You will see many tabs with different URLs. Every tab represents an active WebRTC session. We have to look for something like localhost:8888/peertest.html. As you can see, the page is full of events we have already seen in this video course. For example, if you expand the setLocalDescription event, you will see the full SDP message sent as offer by the first peer connection object. But we don't stop here. Scroll down and expand the last event, It should be named ICE connection state change. As you can see, once you expand it, it reports the status message ICE connection state failed. This is because we've just found the error. Of course, in this case, the error is a bit more difficult to understand. However, we can imagine it's related to ICE connectivity for the first client, since we opened the first tab. We're done here, but don't stop exploring the panel looking for statistical data, past events, and so on. In the next section, we'll create our first complete WebRTC application using all the APIs we previously analyzed. We just learned how to establish a media connection between two hosts. By the end of this section, you will be able to handle Google App Engine channels communication. Upon completing this video, you will discover how to handle media handshaking through messages exchanged via Google App Engine channels. With the GAE Channel API, we'll see how to correctly develop the first two servlet classes that are required for the backend project. Open Eclipse IDE and create a brand new App Engine project. Deselect the checkbox for creating sample code. We won't need it. We'll start developing the services using Channel and Presence API for interconnecting remote clients. Presence is a special feature of the GAE Channel API. The server will be triggered when a client connects to or disconnects from a channel. Then, we'll create our first servlet class to handle channel disconnections initiated by clients. We'll choose a superclass, not the standard java.lang.object, because this class will be reachable from the web through our servlet container. We'll declare it as superclass javax.servlet.http servlet. Name it disconnect page. We need this class to handle client disconnections, as already discussed. After that, we can start overriding the default doPost method, removing the invocation of the superclass method. We have to override it because we're supposed to develop a client, in our case, in the JavaScript language, that will connect to this backend by HTTP post messages. Now, let's start using some channel API methods. However, first we have to remember about logging, so we have to declare a static final variable in which we'll place the reference of the logger instance. After that, just type in log messages and what we'll expect to do. Received channel disconnect. Now, as you might have learned from previous sections, the Google App Engine channel is mostly used in conjunction with HTTP post messages. Basically, the client sends messages via HTTP posts and receives them through the GAE channel. So why do we need a service that intercepts the disconnection messages from clients? The answer is simple. We need it because the server that handles the intercommunication between two clients must know when a client disconnects so that the other client is ready to talk with someone else. We invoke the static method getChannelService of the class ChannelServiceFactory to get an instance of ChannelService. After that, we'll use this instance to parse the presence contained in the HTTP post request. We simply call the parsePresence method's HTTP servlet request object. Finally, we print the client ID contained in the request. We have to stop here for the moment, because in order to move on to the development process of this class, we have to define the data structure and respective classes first. By the way, we can start developing the other class that will use the GAE Channel API. Create a new class extending the superclass HTTP servlet and name it MessagePage. After that, override again the doPost method, removing the invocation of superclass method. Again, we have to get an instance of the logger service and store it inside a static variable. Directly inside the overridden method, we will look for the global identifier for the client's current communication. This ID will be the same for both users, so to better understand, we can name it room key. Then, we have to parse the request's input stream with a custom method that we'll define later. This method will take all the content from an input stream and place it inside a string. After that, we can finally print the received message into the log. Finally, we can develop the custom method for parsing the input stream of the received HTTP post request. So, create a new private method named readBody. Check if the input stream is null, and create a new buffered reader, giving that input stream as argument. After that, we can iterate reading the input stream, line by line, and concatenating all the lines into a single string. After developing the first classes that will use the presence feature included in the channel API, we have to declare to the platform that we want to use custom features such as channel presence, which is disabled by default. For that reason, open the appengine-web.xml file placed under the web-inf directory under the war folder. As you can see, the file acts like a configuration file for the application. It contains the app ID as first parameter and the version. Through this file, we can declare whether our app is developed with the thread-safe methodology. In that case, the platform will send multiple requests at a time to the defined servlet. It also defines the logging properties file and some other useful options. At the end of the file, we can thus declare the disable feature that we want to use, the channel presence option. To do so, open an XML tag named inbound-services. Then open a new tag named service and write the name of the service, in this case, channel_presence. Now, close both the tags. We're done. Now the platform knows which service we need to correctly execute our application. In the next video, we'll see how to create a dynamic ID and manage unique session identifiers to handle intercommunication between users. Upon completing this video, you will discover the basic entities that we'll use as base data entries for our backend project. We'll create dynamic IDs for users' identification on groups of 2 participants that we'll call room. Open Eclipse IDE, create a new class inside the previous project, and name the class room. The room class will be our serialized class to store in GAE data store, so we don't need to extend any additional superclass other than the object class. First of all, we need to define the variables that will hold the real data inside our class. So, we declare 2 strings attributes for storing user ID. After that, we need to declare 2 global variables to store the data store service, and the target object entity to save into the data store. Finally, we declare also 2 final static attributes for holding 2 strings that will be used as a reference inside the data store. After this step, we need to define a class constructor. We're going to define 2 class constructors to simplify the object creation. The first argument will always be the data store service. The second one depends on the data we already hold. We can create an empty room by giving only 1 string parameter as argument, the ID of the room. Alternatively, we can create the room by passing an existing entity made of some users. Then, let's define some class methods that are required to handle the data store. First, we have to define a utility method to update and handle the entity's consistency. We're going to create a distinct method to add users to a room and write that room on data store. So, we need an additional method that updates the entity according to the current state of the room before making the changes persistent on data store. As you can see, we check whether the user is equal to null before adding it into the entity. Otherwise, we remove it from entity. Then, we need to define the real method that will be invoked from inside the class to make the changes persistent. So, we define the put method that will put the entity into data store and the delete method that will delete the entity from data store. Now, we are ready to define the user management methods. We need a method to calculate the room occupancy. Then, we need a method to request the users participating in a room, and then check whether some user is already a participant for the current room. As you can see, their implementations are really simple. After that, we can develop the real methods to add or delete a user. The add_user method checks whether the position for assigning user 1 is available, and then tries with user 2. Otherwise, it will throw an exception. The removeUser method checks whether the user is not null. If it's equal to user 1 or user 2, it will make one of the two attributes null. After the test, it will get the room occupancy, and only if it's more than 0, the method will store it in data store. Otherwise, it will delete the entity. After that, we have to develop the last methods of the class. They are only utility methods with a very simple structure. The most important method is the static one. It will let us query for a well-known room using its key name. As you can see, we use the get method of the data store class applied to the room key object, created using the given key name. Please pay attention to the make_token method as well. We'll use it while developing the core of our backend service. We'll use this kind of a custom token for unique identification of the coupled room and user. At last, we can now define the method to generate a unique room key using a random number generator and a special function. As you can see, in the generate_unique_room key method, we keep iterating while the key is null. However, this is true only in the first iteration or while the room object returned by get_by_key_name is not equal to null. As you can imagine, this is the case when a room with the same recently generated key was already added to data store. So, we keep iterating while a new, not previously generated key will be created. Finally, we'll return that key. So we're done. We completed the room class that will be the base entity we'll use for storing the most important data into the data store. In the next video, we'll see how to correctly develop the core of our backend service. Welcome back. Upon completing this video, you will learn how to develop the core of the backend, handling the main process of user and room creation, and the JavaScript client configuration. We'll develop the main servlet class that will handle the whole process of client configuration and the first user connection. So, open Eclipse IDE, create a new class inside the previous project, and name the class main_servlet, as we did before. This extends the HTTP servlet class and overrides the doGet method, not the doPost one. Don't forget to remove any call to the superclass method. As done before, start by requesting a reference of the logger service. Then, log the current GET request. After that, we can take the room key from the current request. From the client side, we have to remember that we need to place the room_key string inside the GET parameter identified by the letter R. Then, just request the reference to the data store service and check whether the room key received from the HTTP GET request is null. If this is the case, we have to generate a new random key and check whether it's unique. After that, we have to redirect the user to the page with the correct GET parameter. You will notice some errors for undefined methods, for example the sanitize and getBaseURL methods. Don't worry about them, we'll define them later. Now, we have to define two variables, one to handle the user ID that we'll generate, and one more to handle the current user action into the future communication. The variable initiator will be given to the client as configuration, to choose which of the two users will start communicating with the other one. Then, we try to get the current room object from the given key. If the object returned is null, we assign an ID to the user. Then, we create the room, and finally we added the user to the room. In this case, the initiator will be 0. This means, by our convention, that the current user will start the communication. Otherwise, if the room is not null, this means that there's already someone participating in that room. If the occupancy is equal to 1, we need to add the user to the room and set the initiator variable to 1. The current user doesn't need to start the communication process. He has to wait for the other user's request. In case the occupancy is not equal to 1, this is the case in which the room is full. We need to send the error through HTTP 400 error. Now we're ready to display the HTML page prepared as response. We first declare some string variables, for example the link to the room web page. Then we create the App Engine channel token that the client will need to communicate with the backend. Also, we have to give a valid peer connection configuration to the client. For this reason, we invoke a custom make_pc_config method that we will create later in this class. Finally, we read the content of the template HTML page directly into a string. Now we're ready to apply this variable to recently loaded template. As you can see, we apply the replaceAllString method and we use the name of the variable into a double couple of curly brackets to avoid unattended substitutions. Please note that the template.html file will be the container of our JavaScript client application. We'll see how to develop it in the next section. Now we're ready to complete the class development by introducing the missing utility method we used in the main function of our servlet. As you can see, getBaseURL is a simple function that checks the port number used by the server to correctly change the base URL used in the client configuration. This method could be useful for local testing of the app. In fact, the server will run on port 8888. The readFile function is really simple and consists only of a few instructions for using a file reader object to read groups of bytes into a byte array output stream object that we will convert to a string by the end of the method. The sanitize method will clean the room number in case of improper usage of the web service. Finally, the make_pc_config method will configure the peer connection client, writing the options directly in the JavaScript client web page. As you can see, the method accepts 3 parameters. First, an array with custom stun servers, and then the server and respective credentials of turn servers. The method adds the free and public stun server of Google by default. We're almost ready. Our backend is almost completed. We just have to correctly map the external web page's URL to the respective servlets. In the next video, we'll see how to correctly map the just created servlets with the HTTP URL that we'll use in our JavaScript web client. Welcome back. With this video, you will discover how to easily map web URLs to specific servlet classes. We'll see how we can finally map to custom URL all the servlets we've just created using just one file. Open Eclipse and navigate to the web-inf folder under the Word directory. Then open the web.xml file. This will be the file that we will use to map the recently created servlets with custom URL. As you can see, it's a simple XML file filled with XML namespaces. Now let's start defining our first mapping. First, open a servlet XML tag. Inside this tag, without closing it, create 2 children tags, servlet name and servlet class. In the servlet name tag, we have to put the name of the servlet. So, in our case, if we want to map the just created main servlet, we have to place the word main servlet inside the tag. In the servlet class tag, we have to put the fully qualified class name, including the package. So, in case of main servlet, we have to set it to it.alexword.opentalkie.mainservlet. After filling these 2 tags, we can close the servlet tag. We can now open a new tag container named servlet mapping. In this tag, we have to create a child tag named servlet name in which we have to put the name of the servlet we want to map, for example, main servlet. Then we have to add one more child tag named URL pattern. Inside that tag, we have to place the URL path that we want App Engine to map to our servlet class. For example, in case of main servlet, we have to set it to the root of our web service, so we simply type a slash. We can repeat the same process for the disconnect page and message page servlets. However, in case of disconnect page, we cannot use custom URLs. We have to write a well-known URL reported into API documentation page. For disconnect page, the pattern URL tag field will be /ah/channel/disconnected/. For the message page, we can instead use a custom URL, for example, /message. We just need to remember to use the right URL while we develop the JavaScript client. One of the most important features of multimedia communication over the internet is security. We want to build a multimedia application that is secure and powerful. To achieve this goal, we have to use secure protocols. WebRTC has built-in active security methods and protocols when the communication is almost established. However, the developer is responsible for the signaling, so we must ensure that the messages exchanged during the signaling are kept private. For this reason, we have to enable on the server the security constraint for all the content. To do so, we use the security constraint tag, in which we define web-resource-collection with the URL pattern /*, which means apply this constraint to all the served content. Then we have to use the user-data-constraint tag to define the transport type to use. We have to fill it using the value confidential, which will enable the server to serve pages using the HTTPS secure protocol. So we completed our web.xml file. Now App Engine will be able to serve any request coming to our backend service. As we can now understand, our backend service is almost complete. However, if you remember, development of the message and disconnect pages was left incomplete, because we delayed their development after defining the data structure for saving rooms and user states. So, open the disconnect page class to continue the development. First, we have to get the client ID from the presence object taken from the incoming request. We place it in a string named key. If the client ID is not null, we start splitting it into two strings, the room and the user. We saw in the previous video that we created the client ID combining the room and the user ID using a slash. Then, to avoid duplicates, we check if the room actually contains that user. Before deleting, we request the other user, if there is any, and we send him or her a message announcing the disconnection process. As you can see, sendMessage invoked on channel service reference object accepts as arguments the message and the client ID to use. In our case, it matches the token created through the joining of a room and user. That's all. We're done in the disconnect page class development. We can now move on to the message page class. Open the class to continue the development. First, we have to get a reference of the data store service in order to get the room object using the name sent through the HTTP request. If the room is not null, we request the other user and we send him or her the message sent through the HTTP request. Otherwise, we print an error message and send a response back to the current user. Okay, we just completed the development of our backend. In the next section, we'll see how to develop the JavaScript client that will interconnect with the just created backend service. So far, we've learned how to build the backend of our application. In this video, you will learn how to create the basic template for our client application while supporting the HTML5 video container. With our limited knowledge of HTML, we'll create a basic structure for rendering the media objects that represent the current multimedia communication. Start Eclipse and create a new HTML file named template.html under the Word directory. Start creating the main tags for an HTML page. Create the HTML head and body tags. Place a title tag inside the head tag and give a name to the web page. Now we're ready to create a new structure for the container that we'll use to organize our media elements. First, we create a div HTML element named container. Inside that container, we create two other div elements named local and remote. Finally, inside the remote div element, we create a mini div element. We need this particular structure because until the communication begins, only the local div container with the originating user media will be displayed. When the communication starts, we'll show the remote div container that will stream the remote media and show the local media in a mini container inside the remote one. Now we're ready to insert the real media elements containers. In every container, we'll put an HTML5 video container. As you can see, the local video and mini video containers will be muted. We don't want the user to hear the audio. For every video element, we set the autoplay variable because we want to play the local or remote stream immediately when they'll be available. Then we need to add two more containers. One for the button that will close the communication in case the user wants to disconnect from the current session. Then we need to define a console div element that will contain every log that will print to debug our client's application. As seen before in the App Engine backend development, the server has to set some configuration parameters in the client. For example, the room name, the token for using the Google App Engine channel, the initiator variable that lets the user choose if he has to start the communication or he has to wait for the other remote party, and so on. We also need to set a timeout to call an initialization function that will start the communication process. We need to set a timeout function to allow the browser to fully load the contents of the page. Now we're ready to define the JavaScript libraries that we'll need during client development and usage. First of all, we'll need the Google App Engine JavaScript library for better interfacing with the previously developed backend. Then we'll need the client library that we'll develop during this section. The library doesn't exist yet, but we'll start to define it here. Finally, we also place a link HTML tag with a reference to the room_link. We replace it in the backend. Now, in order to better place and display the elements in the web page, we can define a custom CSS style sheet. For this reason, we can use a simple inline CSS definition that will better fit every element in the page. You will notice an element ID named HangUp, which is not yet available in the HTML page. It will be the style for the HangUp button that we'll place inside the button container's div element. That's all. We're ready to develop the client library because the web interface is ready to use. In the next video, we'll see how to properly open a Google App Engine channel from the JavaScript side. Moving on, in this video you will discover how to properly open a Google App Engine channel from the JavaScript side. Start Eclipse and create a new folder named JS. And create inside a new file named main.js. This will be our JavaScript client library, where we will place all the methods and functionalities to start the communication process. Let's do that. We'll define some variables for using them in the next methods. For example, we declare some variables to store the HTML video objects, some variables to handle the local and remote streams, the channel, the peer connection object, and a message queue, and some Boolean variables to manage the application. We also need to set the SDP constraints to receive audio or video. Then we need to create the initialize function to set up the SDP constraints for receiving audio or video. Then we'll need to develop the main function of our client by taking a reference of the local, mini, and remote video HTML object. Only for local video, we set a callback to handle window resize as well. In case of window resize, we will resize the local video object size as well. Please note that we'll develop this function in the next videos. Now we have to call some methods for the following operations. Hide the call HangUp button, open the GAE channel, get users media, and set the default auction for the client. Here, the client is the call initiator, so the one who begins the communication, or else the caller. Now, we are ready to define some utility methods that we've used before. The hideHangUp method will reset the content of the button container. The logThis method will log the current message warning or error directly on browser JavaScript console and on the console HTML container. The window.onResize, instead, will first compute the current window aspect ratio, and then it will set the right size for the local and remote video objects. We are now ready to create and use the JavaScript channel API, which will be the main purpose of the openChannel function that we will create. First, we have to create a new channel object by passing as argument the channel token generated and sent by the server. Then, we have to define the callback methods that will be invoked on well-defined events. Finally, we can open the channel by passing the handler array as argument, which contains all the callback functions and will return the socket object. Then, we have to declare the callback methods executed in case of events. In the onChannelOpened function, we log an event and call the startCommunication method. In the onChannelMessage function, first we decode that message. Then, if we are not the initiator and the communication is not started yet, we start the communication only if the incoming message is an offer message. Otherwise, we will put it on the message queue that we defined before. If the communication is started or we are the initiator, we have to process the signaling message. In case of error, or if the channel closes, we only write some log messages. Finally, we will define the method that we'll use for sending outgoing messages to a remote party through the backend server we developed earlier. As you can see, we'll use a simple XML HTTP request method to send the message. In particular, we'll use requests of the type POST. So that's all, we have finished for the moment. In the next video, we'll see how to properly request media access through the web browser using the MediaStream API. Hello again, and welcome back to yet another video on creating our web application. By the end of this video, you will learn how to request media access through the web browser using the MediaStream API. We will continue editing the JavaScript file named main.js. We are now ready to define the doGetUserMedia function. We request the media passing the constraints. In our case, these constraints are defined in template.html. Video and audio are set true. We use two callbacks in case of error or success. As you can see, we also need two callback functions to handle the success or error of the user media request process. In case of success, we can simply request starting the communication process. We see that the first action will be the media codecs signaling. Otherwise, in case of error, we log some messages. Before starting to develop the peerConnection object, we have to create some other utility methods. If you remember, in the previous video, we created the method named hideHangUp to hide the button needed by the user to terminate the communication. However, we also need a method to show that button when the communication is established in order to allow the user to choose when to terminate the call. The two methods that handle the state of the hang-up button are used inside three different methods that will handle the client's entire appearance during the communication establishment or termination. We have to first define the transition to active method that will show the remote video object, the mini video, and hide the local video container. Please note that the local video will also be displayed on the mini video container. In case of transition to waiting, the method has to show the local video in the bigger container while hiding the remote video object. The transition to done method instead is used to hide all of the objects on the screen. It will be invoked when the user stops himself the communication by pressing the hang up button. Finally, we override the default method onBeforeUnload for explicitly calling the socket.close method. This will trigger on the backend server the method for sending the bye message to the remote party. This will notify the closing of the communication. That's all for now. In the next video, we'll properly start the communication using the peer connection object. Hello everyone, and welcome to another video of Learning WebRTC Application Development video tutorial. In this video, you will learn how to use the peer connection object and how to handle the incoming events through callback functions. We'll see how to handle incoming ICE candidates, remote streams, and signaling messages exchanged through GAE channels. First of all, start Eclipse and continue editing the JavaScript file named main.js. After acquiring the media resources, if that hasn't been done yet, and when the signaling, local stream, and the channel are ready to be used so that we can create the peer connection, we can then add the local stream to the just created peer connection object. We will put all of this stuff into the maybe_start function. Finally, if the client is acting as the caller, it will execute the doCall method. Otherwise, it will execute the callee_start method. Now, we have to take a look at the createPeerConnection method. We need to develop the method that will handle the creation of the peer connection object, the createPeerConnection function. First, we have to create a new peer connection object with configuration taken by the server, thanks to the template.html file, but without any constraints. Then, we set the callback to handle ICE candidates. In case of any problem, we catch and log the errors. Finally, we set two callbacks to handle the stream added or removed. As you can see from the previous method, we need three different callbacks. First, we need to create a callback to handle the ICE candidates received from the turn_stun server. Once we receive an ICE candidate from the stun_turn server, we'll forward it to the remote client through the Google App Engine channel. Then we need to create two more callback methods to handle the remote video when it will be available. In this case, we set the remote video objects with the remote stream URL, and we move the local stream from the local video container to a mini one. In case of a stream removal, we simply print a log string. As you may remember from the previously developed function maybe_start, we define the behavior of the client to the initiator variable, choosing if the client will initiate the communication or not. The doCall method starts the conversation with the other client, creating the first SDP offer. The callee_start method will start to process the received messages, taking them off the channel queue. Just to complete our client, we have to define some additional utility methods. One of them is the process signaling message method. As you can imagine, this method is used by our client to handle incoming signaling messages exchanged through the GAE channel. If the received message is of the offer type, which means the remote client sent an offer with audio or video codecs SDP, we set the remote offer in peer connection object through the setRemote function, and then we answer through the doAnswer function. If it's an answer message, which means we received an update to our offer, we only need to notify the peer connection object about the received reply. If it's a candidate message, which means we received an ICE candidate from the remote client, we pass it to the peer connection object that will handle the choice of the best one. Finally, if it's a bye message, it means it's time to close the communication. The client is disconnecting. Finally, we have to develop the last utility methods needed and some other callbacks. Most of them will only log some text state message. Some others will help the client to reset the communication state after hangup or to forward messages from remote parties. That's all for now. We just completed our JavaScript web client. In the next video, we'll see how to properly start the application and test it. Let's move on. Upon completing this video, you will learn how to briefly test the whole system through the Google Chrome web browser. The best way to see if everything checks out is to just go to the server URL and see if the application is working. Start Eclipse and right-click on our video call project folder. Then select Run As and select Web Application, which should have a blue Google icon. As you may remember from the previous videos, you can monitor the start process from the Eclipse console tab. Open the browser, then go to the URL http://localhost:8888 and let's see what happens. As you can see, in the address bar, we placed the address without inserting a room number. The backend server generated a new one for us. First, the browser, on behalf of our web application, will ask for access to the webcam and microphone resources. On the left-hand side of the window, we can see the logs printed on the foreground. After allowing access to media resources, the application will display the media allowed in the previously defined local media container. After that, the client will simply wait for incoming requests from the remote party. The conversation is not started until a user connects to the same address we see in the address bar. So, we are ready to simulate the remote client. Just copy the address displayed in the address bar and place it in a new browser window or tab. As you can see, just like we experienced before, the browser will ask us permission to access media resources. So, in the left-hand side window, we have the local and first session. In the right-hand side window, we have the remote simulated one. Just after allowing media access to the user, we can see that the communication process begins. Peer connection object is created, then the SDP messages are exchanged. Finally, the remote stream is available on both sides. From a graphical point of view, we can see that the local video has been moved to the new layout in the mini media container, while the remote one has been placed in full size. Also, the Hang Up button has been displayed at the bottom of the window. If we try to push the End Call button, we can see that the communication is interrupted because the other client is informed of the disconnection process. So let's try to disconnect one of the clients. In the logs of the first client, where we pushed the End Call button, we can see an info log displaying some text, reporting, for example, that the channel has been closed. On the simulated remote party, we can see the bye message that will trigger the disconnection process on the remote party. As you may remember from the development in the previous videos, we have already seen that, in case of disconnection, we trigger the sending of bye messages through the socket closing on Google App Engine channel. So, we can see the message only on the receiver side and not on the sender side, because in that case, the sender is our backend server. So that's all. We just correctly tested our full WebRTC application. You can feel free to explore and test it. By the way, remember every tool shown in the previous videos and sections to better handle problems and errors eventually encountered. In the next section, we'll see how to properly create and test a WebRTC data channel. In the previous section, we learned how to create the front end of our application. In this section, you will learn the main differences between WebSocket or AJAX channels and WebRTC channels. To understand and discover the main features and differences between these technologies, our expertise on JavaScript and server-side development will come in handy here. As we are aware, dynamic web pages need to update content automatically without reloading web pages. So, the AJAX methodology was introduced to exchange data with a server to upload parts of a web page without reloading the whole page. This kind of updates will make the app faster and more responsive. Also, if the XML word is part of the AJAX acronym, the JSON container is more often used as data container. The XML HTTP request method is the main method used for placing HTTP requests. These requests could be synchronous or asynchronous. Of course, asynchronous requests require backend functions. WebSockets technology was introduced to create real, full duplex channels between a client and a server. It's because of this new technology that the client can place asynchronous requests to a server and wait for its answer through backend functions. However, as we already anticipated, the connection is fully duplex, because the server on its own could contact directly the client through this kind of socket. This technology consists of a WebSocket object created and used for placing HTTP requests. The most commonly used data container is JSON, like the AJAX technology, which is used for exchanging messages and data. So what about connecting two clients through the just seen technologies? As we can see from the example diagrams, both technologies require a centralized server that receives messages or data from a client and forwards that data to the other client. Let's analyze what is a WebRTC data channel. It's a WebRTC-based technology for high-performance and low-latency peer-to-peer connections between two clients. The data could be shared as blobs or array buffers. Even if the initialization is more complex than other technologies and not well supported at all from every web browser, it's the most convenient way if you're already using WebRTC application. So why use WebRTC data channels instead of WebSockets or AJAX requests? First of all, AJAX requests are not fully duplex. This means that if the server wants to send messages to the client, it can't like this. It has to wait for the client to poll it again, requesting something. We've seen a similar scenario for the previous web application we developed. As you may remember, the client could communicate with the server through HTTP post requests sent with AJAX. The server could send back new messages to the client only thanks to the Google App Engine channel. Regarding WebSockets, they have to pass through a centralized web server anyway. In this case, we might have bottleneck and privacy problems to handle properly. So, WebRTC data channels are the only way to gain real peer-to-peer connection between two peers obtaining full bandwidth usage. The server, in this case, as you can also see from the slide's diagram, will handle only signal forwarding between the two peers, and these signaling messages are usually lighter than the real data that will be transmitted through WebRTC data channels. Finally, we can achieve a safe and private communication thanks to SSL and peer-to-peer features of the WebRTC communications. Okay, that's all for now. In the next video, we'll see how to properly create and use a WebRTC data channel. By the end of this video, you will discover how to properly use the WebRTC data channels in a similar way. Following on from what we learned in the previous videos, we'll now learn how to use the WebRTC API to create data channels. As said before, the WebRTC data channel creation requires some complex configuration and initialization. In particular, we will need a previously created peer connection object on which we will invoke the method createDataChannel. This method accepts as arguments a label and a data constraints variable. Please note that the peer connection signaling should not be in the closed state, so the signaling should be completed and accepted. Let's look at the various attributes supported by the RTC data channels. After data channel creation, we can check the label, see the chosen protocol, check whether the data channel was already negotiated, and we can also set the four main callbacks that will handle the data channel events. The onOpen callback is the function that will handle the opening of data channel. We can set in this function the real core of our channel managing engine. The onError callback is the function that will be called in case of any error on data channel. As you can imagine, the onClose and onMessage callbacks will represent the functions invoked when the data channel will be closed or will receive a message respectively. Finally, let's talk about the most important methods of the data channel object, the send method. As we can see from the API, the send method could be invoked using different types of data objects: DOM string, a blob, or an array buffer. You can choose the version of the send method that fits your requirements best. The most important attribute of a data channel object is the readyState variable. This attribute is read-only and reports at any time the current state of the data channel. Its state could be connecting, open, closing, and closed. This type of attribute could be used to check the current channel state during the event's triggering. In the next video, we'll see some use case scenarios and what kind of web browser is compatible with the WebRTC technology. Welcome back. Upon completing this video, you will discover the various use cases for WebRTC data channels and the browsers that support it. We will also explore different examples of using WebRTC data channels. Usually, when people refer to the WebRTC technology, they assume of an audio-video application used mainly as messenger with a chat functionality. The only services mentioned are voice, video call, or chat ones. The data part is more often associated as an additional and sometimes optional service. WebRTC data channel, on the other hand, could be used to create standalone services and applications that can use the peer-to-peer functionalities as their core value. As you can imagine, one of the first scenarios for WebRTC data channels is file sharing. As you may remember, WebRTC data channels are peer-to-peer links made between two peers. Using data channels for file sharing could ensure file transfers without any file size limits. No central server would be required, so we'd have more privacy and powerful bandwidth performance. This service works as a one-to-many sharing app. It eliminates the need to upload a file to a central server, such as Dropbox, Google Drive, or so on, because it uses the available bandwidth only when the remote clients connect and request those files. Even if the connection will be peer-to-peer, this application needs an intelligent server-side backend that coordinates the various connections and, as you can imagine, handles the signaling process. This online service is also based on WebRTC data channels. It works similarly to our previously developed application. It has rooms with participants. Once you join a room with multiple users, you can send text messages, so there's a chat functionality, and share files with all the members of that room. Imagine a torrent client fully working through WebRTC technology. You wouldn't need any client plugin or software installation. The online torrent search engine, indexer, or aggregator could host this JavaScript client that would run directly inside the browser. Imagine streaming a video file directly from the torrent network inside your web browser in a video tag. We wouldn't have any problem of NATing because we'd have the ICE protocol directly implemented inside the browser, as the standard of WebRTC technology has. You would extend your web browser feature in a moment. WebTorrent is a project that aims to create a fully working BitTorrent client inside a web browser. It's written entirely in JavaScript and using the WebRTC API as well. Currently, the authors made some protocol changes to better adapt to the current web browser's limitations and to use the latest WebRTC API. At the moment, the current development app version enables your browser to only talk with other WebTorrent clients. However, the authors have already thought of a simple workaround: the use of a hybrid client that translates the current protocol changes to allow WebTorrent clients to work with non-WebTorrent clients. The Content Distribution Network is a special network of servers that scale and distribute many HTTP requests to a web server. Using WebRTC data channels through peer-to-peer connections between the same website's visitors could help the loaded website to easily scale its load and improve its performance. Imagine that a client is connected to a well-known website, and then another client comes to that website. With an intelligent server, the second client could request the resource not only to the server, but also to the previously connected client. This would reduce the load and bandwidth consumption of the server, reducing its management cost. PeerCDN is a popular example of peer-to-peer CDN through WebRTC-capable browsers. It's fully written in JavaScript, so you don't need any additional plugins. As mentioned before, you'd be able to handle traffic burst by sharing the load request with the connected clients. More visitors will correspond to more peers for sharing the load. This is because WebRTC is supported by Chrome and Firefox has an almost complete support of the available browsers in the net. As already told, WebRTC is fully oriented and developed for privacy-safe application, thanks to its well-adopted security standard. So why not use it to develop a secured search engine? Using only one technology, we would have the best security protocols for protecting user data, ICE support, and brand new functionalities. Blipex is one of the first web search engines to use WebRTC data channels to protect its user data from unauthorized access. Blipex provides users, in an anonymous and secure way, the URL and time spent on sites that they visit. This usage data is sent through a chain of peers. Also, the data is made of unpredictable length, and the URL and time information is encrypted, so no one in the chain can spy on it. This way, Blipex managed to create a search engine that is constructed by users' behavior and interest. Thanks to Blipex, you will find the most interesting results in the online community. In the next section, we will develop a working example of a chat and file sharing application using the just introduced WebRTC feature, the data channel. Hello everyone, and welcome to a new section of Learning WebRTC Application Development video tutorial. Upon completing this video, you will learn how to handle WebRTC data channels by simply editing and adapting the previously developed client. Thanks to the previous knowledge of WebRTC peer connection object, we will see how to manage data channels and what we need to change in the code. Open up Eclipse, then copy the main-servlet.java class and paste it in the same container. Eclipse should ask for a file name. You should give it the name data-servlet. After that, open the newly created data-servlet class file and start editing it. As you may understand, this brand new servlet should use a different URL for request-backed services. So we should define a new URL. We can use the keyword data just after the website root. For this reason, we should look into the file for all the variables reporting the website root URL. As you can see, the first variable to change is in the doGet method, and it's named redirect. We simply add the keyword data before the question mark. However, please note that we have to assign a URL mapping for this new server, with URL using the keyword /data in the web.xml file. Then we edit the variable named room_link, which we pass to the web client as a configuration option through the HTML page. Finally, the HTML web page template, which we will create from scratch to better support all the new functionalities we will develop. That's all. We have finished on the backend side. As you can see, the editing was minimal, because this kind of servlet is only responsible for handling the signaling through the chosen HTML web page. Once we change the URL of the servlet and its serving HTML template file, we're done. Duplicate the template.html file as you did before, then copy and paste it in the same location. Eclipse will ask you for a new name. Give it the name template_data.html. Then open it up. After that, start editing the template matching its first usage, data channel handling. First, we change the web page's title and give it a different name. Then, we place inside the page a brand new CSS according to the tags we will use here. After that, we remove the media constraints from the respective array variables. In this case, we only want to send and receive data through a peer connection object, so we don't need to ask media resources access to the user. Then, remove both the IDs with IDs container and button container. We won't need them anymore. We are in the process of defining new HTML structure and style. We leave the console container to print some logs. Finally, we also add a new variable named data constraints, which will handle, if necessary, any constraint we want to give to data channels. Now, we need to define a brand new HTML structure. Let's create a div named wrapper, inside which we place another container named menu. This has two paragraph containers, in which we will write down some information about the connected user and the button for leaving the app. Now move on to the JavaScript side. We can do the same thing as before. Copy and paste the main.js file and create a new file named main_data.js. Then open that file and start editing it. First of all, we don't need the variables local video, mini video, remote video, local stream, and remote stream anymore. So delete them. Also, we don't need the STP constraints variable, because we won't use any additional resources from the user. However, as you can imagine, we also need to add a data channel variable to handle the data channel we will create. It seems we completed our backend. However, if you check our previously executed steps, you will see that we missed one thing. We haven't added the URL mapping for our newly developed servlet yet. We add the URL mapping for the data servlet by defining the URL with keyword/data. In the next video, we will see how to properly create and handle peer-to-peer chat systems based on WebRTC data channels. Hello everyone, and welcome to a new video of Learning WebRTC Application Development video tutorial. Upon completing this video, you will learn how to create peer-to-peer chat systems using WebRTC data channels. Thanks to the previously created HTML template file and its JavaScript library, we will develop a fully working peer-to-peer chat system. Now open Eclipse and continue editing the JavaScript file. We will start editing the JavaScript function initialize. We have to remove all the references about the videos and the hang up button. If you remember, we removed their containers from the web page. We have to remove the call of the getUserMedia method as well. We don't need to request any additional resources to the user. Finally, we also need to remove the definition of the doGetUserMedia and hideHangup functions. Then, since we will use a static HTML template, we don't need any reference of the window.onResize function that we defined earlier. We can leave the function openChannel, which is used to open a new Google App Engine channel. Also, we can leave the following functions that refer to the Google App Engine channel. Now, for the functions related to user media features, we can delete them all. We don't need them anymore. We can also remove the showHangup button function, because we don't use that button anymore. Okay, now let's move to the transition methods. We need to change them according to the editing we did in the HTML template file. First of all, we don't need the old functions content for the transition to active function. We can delete them and place only a method to clear the content of chatbox and enable the input box of the chat. For the transition to waiting method, we need to replace the whole content with a method for replacing the content of the chat box with a standard initial message. Also, we have to disable the chat input boxes. For the transition to done method, we need to replace the whole content with a method that writes a message connection closed inside the chat box and a method that disables the chat input boxes. This method writes down such a message because it's called when user ends the communication by clicking on the exit chat button. We can also leave the window.onBeforeUnload method. We'll need it again to trigger the socket.close method in order to release the Google App Engine channel. Now it's the time for the maybe_start method. As you might remember, this method is mainly used to start all the necessary processes to handle an incoming remote connection or to initiate an outgoing remote connection. In the case of a chat session, we don't need the whole content of this function. In fact, we can remove the local stream variable check in the if statement and also the pc.addStream method invocation, because the local stream object is not used anymore. Okay, let's move on to the create peer connection method. As told before, we don't need any additional resource, so we won't need the callback functions to handle local or remote streams. We can remove them. Now, we need to include all the data for creating the data channel. We will handle any errors, state changes, and messages received. We will develop those functions in this JavaScript file later. Then we can leave the onICE candidate function, because the ICE process still happens and it's fundamental to establish the network connection. As explained before, we removed the onRemoteStream functions. Again, we can leave the doCall and callee_start functions as they are. Then we can also leave the process signaling message function as it is. The working process is the same as before. We can perform the same operation for the remaining functions up to the onHangup function. At this point, we have to rename that function to onExit. And we also have to remove the called method localstream.stop. After that, we can leave the onRemoteHangup method and the stop methods. But finally, we have to remove the waitForRemoteVideo method, because we don't need it anymore. We just completed all the editing necessary for the original main.js file. Anyway, we now have to define all the new methods that will be necessary in the whole process of the chat system. We have to define the methods that we've already used before: enable chat and disable chat. The enable chat message will enable all the chat inputs. The disable chat inStream will disable all the chat inputs. After that, we have to define the callbacks necessary to handle incoming WebRTC data channel messages. The onReceiveMessage callback method is really simple. It parses the JSON encoded message and prints it in the chat box if the data type is equal to chat. Otherwise, it will log a warning. After that, we have to define the callback function necessary to handle any state change of the data channel through the transition functions. Then we can define the sendChatMessage function that will send a message to the remote party through the sendData function. The sendData function will interact directly with the WebRTC data channel. This function will encode the message using JSON and send it through the WebRTC data channel. Finally, we have to complete the create peer connection method. First, we have to create the data channel object. After that, we have to set the callbacks for handling its state changes. That's all. We can now move on to the HTML part. Open the template_data HTML file again. We have to define a div element that stores chat messages. We will name it chatbox and we'll start placing inside it a text that warns the user that the client is waiting for the other participant. Then we have to define two input elements. One to write down a new message and one button to confirm and send a message to a remote participant. Looking at the CSS, we moved the console at the bottom of the page and placed a squared container for the chatbox and the input elements. You can watch the result by simply opening the HTML web page through a web browser. That's all for now. We could also test the result of our hard work, but let's wait for the next video to develop the file sharing functionality first. In the next video, we will see how to properly create a peer-to-peer file sharing system using WebRTC data channels. Hello everyone, and welcome to a new video of Learning WebRTC Application Development video tutorial. Upon completing this video, you will learn how to create a peer-to-peer file sharing system using WebRTC data channels. Thanks to the previously created HTML template file and its JavaScript library, we will develop a fully working peer-to-peer file sharing system. Let's complete the file sharing functionality for our web app. First of all, let's open the template_data HTML file. We have to add the required HTML tag to handle the file sharing functionality. We also have to add an HTML div container for the file sharing input. Inside that container, we place a text message to instruct the user on how the process works. We don't need to define any additional CSS field, because we have already defined it in the previous videos. That's all now. Let's move on to the JavaScript side. We have to add all the required variables that the file sharing functionality might need. We have to define an array for handling the data packets we will receive, piece by piece, from the remote party. We will also have to set the file name, the total bytes, and the currently received bytes for any sent or received file. Then, for better testing our newly developed web app, we have to set some constraints for data channels. If possible, we have to use RTP data channels while creating the WebKit-RTC peer connection object. After that, we have to search for the onReceivedMessage callback, because we will use the same data channel to send chat messages and data files. We need to add a conditional instruction to check if the incoming message represents a user chat message or a file part message. If we receive a file part message, first we check whether it's the first time we receive a part of that file. If this is the case, we reset all the used variables to store the new information. Then we push the data in the array container and increase the saved current size of that array. Finally, if the received message contains the last part of the file, then we print out the local download link to allow the user to save the received file. Otherwise, we print a message reporting the progress of file transfer operation. Then let's move to the enable or disable chat methods. We should adapt them to enable and disable the file sharing options as well. Regarding the enable chat method, first we have to enable the input HTML container. Then we have to set the callback for handling the file choosing process. As first action, we take a reference to the chosen file. Then we take the file name and set up a file reader. Thanks to this HTML5 file reader, we read the data and put it on a blob file. After that, we also define a callback that will be called once the reading process is completed. For the disable chat method, we only need to disable the file input element. Now it's time to define the new functions that are required by the file sharing functionality we just added. We start with the onReadAsData URL function. As you can imagine, this function will handle the reading and sending process by groups of bytes. First of all, we prepare the data container, and then we set the data type to file, in order to signal to the remote party that we're sending a file. We haven't added a reference to the file we're sending into the chatbox container. We will do it now. We'll use this div element to update the user regarding the progress of the file sharing operation for this file. Then we set the file name variable, the total bytes to send, and the current number of bytes we have already sent. In our case, since this is the first time, we set it to 0. After that, we also check the length of the data message. If the data is longer than 1000 characters, we cut the message in more parts and send them slice by slice. In any case, if it's only a status update or the process is completed, we print out a message to warn the user. Finally, we send the data through the same function we defined previously for the chat messages. Now it's time for the print download link function. We pass to that function a file URL and a file name. We can now print out the received file address link, and this kind of link is only a local one and allows the user to get a copy of the file stored on the browser's temporary directory. Finally, we have to map the newly created servlet into the web.xml file. Let's open the web.xml file and duplicate the existing one from main servlet. Then edit it according to the data servlet's name. That's all. We can now start testing the app. First, start the Java backend as shown in the previous videos. Then, open up the Chrome browser and go to http:// /localhost:8888/data. Copy the URL containing the assigned room number from the browser's address bar and paste it in a new browser window. You should see something like this. So that's all. Feel free to try and test this new version of WebRTC application. In the next section, we will learn about the different kinds of WebRTC wrappers and how to use them. Hello and welcome back. Upon completing this video, you will learn what are JavaScript wrappers and what is their purpose. Now that we have acquired quite some knowledge on the WebRTC technology, we will see how and when we can use some JavaScript library wrappers for the WebRTC technology. A JavaScript wrapper is a set of functions that simplifies the usage of some other complex functions. A wrapper acts like a middle entity between the developer and the real objects that the wrapper handles. It could also be used to suggest detailed configuration for a subset of objects, depending on the scenario, or it could be used to hide unwanted features. The main benefit for you, the developer, is that you could reduce the effort and the knowledge required to use some libraries. You may ask, why use a WebRTC wrapper? We use it because it provides a set of functions that simplifies the WebRTC usage. It will handle the object's initialization, and then it will start the client registration and media signaling processes. It will let you create and manage WebRTC sessions in a simple and fast way. So, let's summarize the main activities managed by a WebRTC wrapper schema. The initialization process will place the basic client configuration and it could ask for the user's information. Then, the registration process will take charge of the initialization of external channels and it will start the signaling process. The wrapper will also take care of session handling, getting user media and creating data channels. Finally, it will help developers by filtering and reducing the number of callbacks to manage. As you can imagine, since the initial release of the WebRTC technology, many wrappers have been introduced. First of all, since in the initial phase of WebRTC development the technology was in continuous evolution, the methods and usage was changing fast, and the best way to use its API was to use a well-made JavaScript wrapper. In this slide, we can see only a small number of the WebRTC JavaScript wrappers: API Days, PeerJS, Phono, Simple WebRTC, and so on. Every WebRTC wrapper reported in this page, and in general any wrapper you can find on the net, could help you reach your objectives. When dealing with a brand new technology and when you have very little time to learn as much as possible, the alternative solution could be using a wrapper. Of course, you could also try to integrate this kind of wrapper in any of your projects, and when you feel more comfortable, you could try to switch out to the real WebRTC API, removing any reference to that wrapper. Or maybe build your own wrapper. In the next video, we will see the main features of the PeerJS WebRTC wrapper, and how to properly use it to build a working WebRTC app in a simple and fast way. Hi there! Upon completing this video, you will discover what is PeerJS, its purpose, and its usage. Thanks to the previous sections, we will understand the main uses of this library and also see some examples. As anticipated before, PeerJS is a WebRTC wrapper that provides an easy-to-use tool for wrapping the API contained in the browser. Thanks to an assigned ID, two peers can communicate with each other, transferring audio or video, or simply creating a data channel for file transfer. Now, open up the PeerJS documentation. As we saw, to use PeerJS, first we need to include its JavaScript library. Then, create a new peer object. We need to pass an API key to the constructor. The example shows a sample API key, but you should request your own by following the procedure. Just continue reading the Getting Started guide. We can see that we can override the PeerJS callbacks method for handling events. For example, the onOpen callback to know when the connection is open. Once a peer is created, it will receive a unique ID. Pay attention here, this unique ID is not the API key, but is used to identify peers in communications. Even if the PeerJS aims to simplify the WebRTC API usage, it can't delete every callback method. In fact, for starting a video or audio call, we should ensure that the current peer is effectively connected to another peer before starting the communication process, in our case, the call. So, we have to use the PeerJS callback method .on matching the open event. This is the main event that will inform us that the communication has started, so our wrapper can take charge of establishing a multimedia or data connection. As you can see, to place a call, we should also provide a media stream object obtained through the getUserMedia method, as seen in section 5.3. Let's open up Eclipse, edit our old template file, and try to get a working client using PeerJS wrapper. First, duplicate the template.html file and then assign it a new name, for example, PeerJS-start.html. After that, open it and start editing. We have to remove any reference to the previous JavaScript file and any dynamic content. To simplify the code, we remove any transition needed by the HTML, creating only two video elements that are always on top of the screen. We also remove the button container. We don't want it. We just want to test the connection. Now, following the Getting Started guide, we will add the reference to the JavaScript PeerJS URL. Then, we will place the code to create a new peer object. We will use the demo key reported in the Getting Started section. We set the debug level to 3 to get less information. Our purpose is to only check whether the app is correctly working. Then, we also place the custom function we developed previously in our JavaScript library, log. We need this function to print the result on both the console and the IB container. After that, we will place all the necessary methods to start placing a call when the connection is available. Please don't forget that in this case, we are creating different web pages that match the caller and the called. So, we will place the code to print the assigned ID, and then we will wait for the incoming call from the other side. However, in order to reply to the incoming call, we will also need a media stream object. So, to avoid requesting it at the moment, we place this instruction as the first step. Finally, to complete the test, duplicate this HTML file again and name it PeerJS-reply.html. Open it and start changing the code. First, we have to get the remote ID that we need to call. As explained before, we divided the caller from the called by using two different HTML files. So, we need to add to our JavaScript a function for taking the HTTP GET variables from our page URL. So, we add the function parseGetValue. We will use it to get remote ID. Finally, we will also replace the handling an incoming call code with the code for starting an outgoing call. Now, we are ready to start testing this little example. First of all, we need to start the local servlet container through the Eclipse Run configuration. After that, we can use the Chrome web browser to go to http://localhost:8888/peerjs-start.html. The web page will request for the user media. Then it will print the received ID through the console DIB container. Now copy that ID and place it in the next tab's URL. Using the next tab, we should go to the URL http://localhost:8888/peerjs-reply.html?ID equal just copied ID. So, if all is working properly, you should see something like these windows. That's all. We achieved a fully working PeerJS client in minutes, without using any of the previously explained methods. In the next video, we will see the main features of a simple WebRTC wrapper and how to properly use it to build a working WebRTC app in a simple and efficient way. We just created a fully working application. Let's move on. Upon completing this video, you will discover what is simple WebRTC, its purpose and its usage. Following from what we learned in the previous sections, we will understand the main usage of this library and see some examples. As anticipated before, Simple WebRTC is a WebRTC wrapper that provides an easy-to-use tool for wrapping the API contained in the browser. We've seen that PeerJS simplifies the process of handling WebRTC sessions. Simple WebRTC simplifies the process much more. In this case, we will see that we can give the video container to the object, and the wrapper will do all the dirty work for us. We could also request more control by using the modules included in the Simple WebRTC library. We can find a list of suggested modules in the Simple WebRTC main page. The Simple WebRTC documentation is not too exhaustive. The library is really simple, so we shouldn't have much trouble using it. As we can see from the main page, we have to include the latest version of the library in our HTML web page. Then, create a new Simple WebRTC object in the JavaScript side of the page. We need to pass to the constructor the two video elements containing local video and remote video. Finally, for an easier configuration, we set the property of auto-requesting user media to true. Now, in order to connect to another user, we see that Simple WebRTC uses the same concept of room that we used before in the web app we developed in the previous sections. We set a callback on a ready-to-call event, which the Simple WebRTC library will trigger when the client is ready to forward calling requests. Then, we will use the join room method for joining a room. Open up Eclipse and let's edit the previous PeerJS-start.html file and try to get a working client using Simple WebRTC wrapper. Duplicate the PeerJS-start file and assign it a new name, for example, simpleWebRTC.html. After that, open it and start editing. First, we have to change the web page title, and then we have to remove any reference to the previous PeerJS library. We also remove any reference to the custom logThis function that we created for logging messages. For the HTML side, we could delete also the reference to the console div element. We don't need it anymore. We also remove the references to video objects. In fact, as we've seen from the main page of the Simple WebRTC project, we need to give to its constructor only the div containers. Inserting the video elements inside their containers will be done by Simple WebRTC library. Now, following the guide on main page, we will add the reference to the JavaScript Simple WebRTC URL. Then we will place the code to create a new Simple WebRTC object. Starting from a recent version of Simple WebRTC, the library takes the port number of the signaling server directly from the one of the web server. Since we host our web server through the App Engine on localhost listening on port 8888, we have to manually set signaling.simplewebrtc.com followed by the port number 443. That is the standard port for an HTTP secure web server. As we saw before, we will also give as constructor's argument the two div elements that will handle the video elements once the connection is initialized. Then we set the property for auto-requesting the media needed for a video call. Finally, once the Simple WebRTC triggers the event ready to call, we will call the join room method to call the remote participant. As you can imagine, placing a static room name will free us of making a different version of HTML page for handling the remote side connection. So, we can open two browser windows that point to the same static HTML page and simulate the local and remote party connection. Now, we are ready to start testing this little example. So, we need to start the local servlet container through the Eclipse Run configuration. In my Eclipse environment, this is already started, so I can skip this step. After that, we can use our Chrome browser to go to http://localhost:8888/simplewebrtc.html. The web page will ask for the user media. That's all. Now, the Simple WebRTC library will wait for an incoming connection, and it will handle the calling process for us. Now, copy the same URL and paste it on a new window. The process will begin silently, and you should see something like this. In the next video, we will see some examples and real projects that use these WebRTC wrappers. By the end of this video, we will get to know real projects that use WebRTC wrappers from the web and see how they work. Now that we have some knowledge on the recently introduced libraries, we will find out how real projects work. If we search for PeerJS projects and examples through the official website, we can see a lot of nice examples that could help us create our new web app. Let's start by clicking on the first example, Simple Video Chat. On the right-hand side of the page, we can see our ID. We'll be reachable through this ID, so we could share this with our friends by SMS, for example, and see them in minutes. Let's open a new browser window and point it to the same URL. After requesting media access again, the PeerJS server will assign us a new ID in the second page. After that, we could copy and paste the first ID and place it on the second page to start the call. If everything has gone well, you should see something like that. As you may remember, this example is very similar to the one we made using the WebRTC and PeerJS wrappers. Let's move to another example in the examples page on PeerJS website, WikiGolf. WikiGolf is an online game that consists of reaching a goal page through the many links of a Wikipedia page. The players who reaches the goal page with less links followed will win. The game also has another purpose. The different choices of the players could help the game's authors to solve complex problems of artificial intelligence. Let's go ahead and try it out. Open two browser windows and go to http://wikigolf.herokuapp.com. Please pay attention. It seems that the server uses cookies. So, for testing the app on the same machine, you should open one normal window and one incognito. After that, click on the Play a Game button on both windows, and the game starts. After a little delay, you should see something like this. Now, let's move on to the simple WebRTC examples. As we can see from its main page, one common example for the simple WebRTC library is the Talkie.io application. Talkie is a very innovative web application that lets you do group video chat, screen sharing, and private room using the brand new peer-to-peer technology WebRTC. It doesn't require any sign-up or payment, and it works on mobile devices as well. So let's try this app. From its main page, give a name to the conversation. After that, the web app will show us a very beautiful interface using which we can access the various functionalities exhibited by the app. So, let's connect one more user. Open up a new browser window and point it to the URL suggested at the center of the web page. After that, you should see something like this on both pages. Also, we can add more than one participant. We can test it with 4 windows. The app should work fine up to 5 participants. As you can imagine, since the application should establish peer-to-peer media channels through each participant, in case of 2 participants, we will have one multimedia connection for each participant of the room. Increasing the number of participants will increase the number of media connections for each peer. So, we have come to the end of the course. I would like to thank you all for watching it. In case of any issues, you can always refer to the documentation links we've seen during the course, or you can check with the many communities related to the WebRTC technology. One more thing, don't hold back your imagination. You can know every technology in the world, but in order to create good and innovative applications, you should apply good ideas. Goodbye, guys.